I'm really enthusiastic about particle physics, and so if anyone's going to give me the opportunity to talk about it, I'm going to take that opportunity. From a pragmatic point of view, the general public funds our research, and our research is not cheap. So if they're going to pay for our work, they're going to want to hear something in return. I think the general public want to hear about our work, and so we need to send that back, what we've discovered, with the money they gave us. And there's a final reason to do it. We need to encourage more people to do physics in general, as well as just particle physics. Science, and more importantly physics, is essential to a healthy economy. And so far, we've really suffered with getting enough people to do it. So these are the number of A-levels sat in 2011, and you can see that more people took media studies A-level in 2011 than took physics. That's not to disparage media studies, but if you want to dig yourself out of recession, you might need more scientists than journalists. The other big problem that physics has is that we have a horrendous gender bias. So in 2011, 20% of the people who took physics A-levels were girls, only 20%. And by the time they reached university, that was 10%. Now, there are many reasons why physics is putting people off, and more importantly, putting girls off. We're still trying to discover all those reasons, and there are many different ways that we can try and tackle those different problems. What I'm going to talk to you about today is just one way in which we can solve the numbers problem. So, when I go and talk about particle physics in schools or to the media, what sort of things do we talk about? Well, the main thing that particle physicists talk about is just how successful our field has been. By any quantitative measure, particle physics theory has been the most successful achievement of human scientific endeavor. We can, for example, measure the strength of the electric force to almost 9 significant figures. This parameter, alpha to the -1, that's just a measure of how strong the electric force is. And while many sciences who predict 137 will be really pleased to measure 137, particle physics can do much better. We can measure not just 137, but 137.03599, and we just differ on that 9th significant figure. This is an astounding achievement to get experiment and theory to match to this degree. Not only because that's an incredible degree of accuracy, but this number is so sensitive to the details of your theory. You add an extra particle to the universe and this changes. You change the strength of one of the quantities in our theory and this changes. And this isn't the only success that particle physics has had. This is the table of particle physics. Some of you may still have horrific nightmares about the periodic table from school. Do you remember all those hundreds of chemical elements with terrible names? They all behave differently. It's impossible to remember. Well, particle physics has saved you. We've done away with the entire periodic table, and with just 17 particles, you can explain everything in that table, which means you can explain the entirety of chemistry and the entirety of biology, and therefore the rest of the universe too. In fact, almost everything in your life can be explained with just 4 or 5 of these particles. And you may notice the one slight blemish in our record is this box at the bottom, which we put a dotted line around, the Higgs boson. You might have heard about it in the news recently. And that's the reason it's got a dotted line is because every single one of these particles has been detected and proved to exist in an experiment, with the exception of this one in a dotted line. But wait, we've done that now. In summer of this year, particle physics announced that the largest experiment ever built by human beings, with the most scientists coming together in peaceful collaboration, have managed to achieve the most data ever generated, the highest data rate ever made in an experiment. All of these things came together, and we've now discovered probably the Higgs boson. We've finished off our theory of particle physics. Everything's solved now. The universe, chemistry, biology, your lives, everything. The world is impressed, and we know it's impressive, and we're left just to sort out the finer details of creation. Okay, if I'm starting to sound a bit arrogant, that's good. But I'm exaggerating. Although, actually, this is often the impression that we give off when we talk about particle physics to the wider world. We talk about the discoveries we've made. We talk about the questions that we've answered, the problems that we've solved, the successes that we've had, and how complete our theories are. And that's understandable. Scientists intrinsically have a fear of being thought to not understand what they're doing. And also, when our experiments cost such a large amount of money, we are very worried about people thinking that that money has not been well spent. Nonetheless, does that sound like a subject in which you have a future? Does that sound like a subject which you have something to contribute to? Let me paint you a different picture of particle physics. Gravity. There are 4 forces in our universe, of which one is gravity. It's probably the one you're most familiar with. It holds you onto the Earth, it holds the Earth together. It holds the moon in orbit around the Earth, and it holds the Earth around the sun. So if I asked you just to pick one force in this universe that you wanted to keep, gravity is quite likely to be that one force. Nonetheless, gravity is not explained by particle physics. Despite the fact that we can predict things to almost 9 significant figures, if you put gravity into our theories, it breaks. Things go to infinity and things fall apart. Certainly our Earth isn't here in those theories. So particle physics can't explain gravity. And that's not the only problem. Every single one of those particles I showed you in the table earlier has an equal and opposite counterpart. So if those particles are called matter, then their equal and opposite counterparts are called antimatter. And in every experiment we've ever done on this planet, matter and antimatter are created in equal amounts. That means that at the start of our universe, in the Big Bang, matter and antimatter should have been made in equal amounts. But this planet is only made of matter. And if we look out into space, no matter how far we look, all we can see is matter. There is no antimatter out there. Half of what is made at the start of our universe has vanished, and particle physics has no answer for where it's gone. That's not quite so impressive, is it? And that's not the only problem either. If we look at the half that's left, we can look at galaxies and see that they consist not just of the matter that we understand, but some additional matter that we don't. We call this dark matter, which basically means we don't know what it is. We can tell you what it's not, but not what it is. And our estimates suggest that 23% of the entire universe is dark matter. Does that sound like a subject that has the finer details just left to do? 23% of the universe is missing. In fact, that's not even the worst thing. If we look even further out and look at the galaxies on the edge of our visible universe and look at how they're moving away from us, they're not just moving away, they're accelerating away from us. They're being driven by some unseen energy, which, because we don't understand it, we call dark energy. Remember, we're already missing 23% of the universe. We estimate this takes up 72% of what is in the universe is dark energy. That means that only 5% of the contents of this universe is explained by that table I showed you earlier. 5%. We understand that 5% very well. We understand it's 9 significant figures, but we only understand 9%. Perhaps we're not sorting out the finer details after all. And again, I've perhaps exaggerated. Particle physics isn't a group of bumbling idiots. These are difficult problems, and their solutions are going to be difficult. But perhaps when we go into schools and we talk to the media, these are the things we should emphasize more. Not the things that we have discovered, but the things that are still to be discovered. Not the questions that we've answered, but the questions we need to answer. The problems we need to solve. The successes that lie ahead. Perhaps that sounds more like something that you can get involved in. Science is exploration. And it doesn't matter how fascinating or exciting or incredible the discoveries we've made so far are, it's what lies ahead that's important, and it's that we should focus on. Now, I focused heavily on science, and I don't know what you communicate or educate about, but you're probably trying to enthuse people about your subject, to get them to support your subject, get them to come into your subject in the same way that I am. So perhaps this is a message that everyone can take home, that if we focus on why someone would want to do that, they're more likely to do it. Because it doesn't matter how incredible what you've done is. People aren't inspired when they hear about what you've done. They're inspired when they realize what they can do. Thank you.